Hello good people and welcome back. In this video we are working on the Black-Scholes and Merton model, and we are essentially doing some practice. Okay, so let's get started, and we are going to start with making a couple of assumptions. Let's say we are working with a security that is priced at $66 today. The interest rate is at 2.5%. The volatility is at 25%, and we seem to 25% here. And we are also working with a what else do we need? Stock price, interest rate, volatility, time to expiration. So we're working with an option that expires in 6 months, and we're going to be working with the call option, and the strike price on the call option is going to be equal to $55. Alright, so that's the setting that we have. A couple of things that we want to get started with is playing with volatility. So let's start playing with volatility here. So the volatility that's listed in general is listed as a an annual volatility. So the volatility is if you're working with the daily returns, then what you have here is that the volatility of 252 days is going to be equal to the 25% that is listed there, and that is essentially to suggest that the annual volatility uses the 252 days per year as a measure of the number of days for the year, and those are the trading days in the year. And so the daily volatility, you should say sigma daily, would be equal to the sigma annual, that's the 252, multiplied by the square root of 1 over the number of days, which is 252. That would be a daily volatility. Now the dollar volatility that corresponds to that, should call that dollar volatility, which will be equal to the stock price multiplied by the annual volatility, that is sigma 252, multiplied by the square root of 1 over 252. Now if we substitute the values here, we would essentially have 66 multiplied by the 25% multiplied by the square root of 1 over 252. And that would give us the dollar volatility in this case, and that would be the daily volatility in this case. Alright, so if we did that, see if I can pull my financial calculator here and do just that. Alright, so what we're going to do, we're going to do 1 over 252, that's 252, equal, that gives us that. We do the square root of that, we multiply that by 0.25, and we multiply that by 66. So that gives us $1.04, and so our daily volatility in dollars will be approximately equal to, should have that here, this would be approximately equal to $1.04. That's going to be approximately equal to $1.04. That would be our daily volatility here. Now if we're working with monthly return, so if monthly returns, then the sigma of 12 month would be equal to the 25%, and what that means is that the sigma for 1 month would be equal to the sigma for 12 months multiplied by the square root of 112, and which means that the monthly volatility, I should see NTH here, the monthly dollar volatility would be equal to the S0 multiplied by sigma 12 multiplied by the square root of 112. Okay, as usual, let's use a financial calculator and do that. So we would have 12 1 over x, square root of that times 0.25 equal times 66 equal, so about $4.76. So we would have about $4.76, approximately $4.76 would be our daily volatility there, our monthly volatility there. All right, so we understand how we could make adjustment to the volatility. So the daily volatility will be computed this way because we have 252 days. The monthly volatility will be computed that way because we are working with 12 months. So the weekly volatility will be computed correspondingly using 52 weeks in the year. Another thing we may be interested in working with this data is essentially computing confidence intervals. And how do we go about computing confidence intervals? We want to remember, so we recall that the log of ST is normally distributed with the mean of R minus 1/2 of variance T, and our, actually there's something else here. There's log of S0 plus the mean, which is R minus 1/2 of variance, and then we have T. There we go. That's the mean of the distribution, and the volatility or the variance is going to be sigma squared T. That is the distribution that we have there, and that's essentially what we're going to be working with. And so if we need to find the confidence interval, we're going to be working with that. Now remember that if we substituted the values here, what do we have? We have the log of ST would be normally distributed, and our mean will be the log of 66 because S0 is 66, plus we would have our interest rate, which is 2.5%. I think we said that here, that was 2.5%. So we would have 2.5% minus 1/2 of the volatility, which is 25% squared, and then we multiply that by T, and the time to expiration of our option we said was 6 months, and that's 1/2 of a year. So that's 1/2 of a year. We will multiply this by 1/2. Okay, and then our variance would be sigma squared. That's going to be 25% squared multiplied by T, which is 1/2, and that will be what we have there. Alright, so with that, if we were to plug in the values and do the math here, I would essentially do, let's do this, let's use a different color here. We would do STO0, and we'll do STO1, and then we'll do ST1 plus STO0. And so let's pull a calculator and do just that. I'm going to create a memory first. So second memory, I'm going to get rid of everything. So second clear work. And what do we have? We have 0.25 squared. We're going to divide that by 2. So divide that by 2 equal. Let me verify that I did that correctly. 0.25 squared. I'm going to divide that by 2 equal, and I'm going to do minus, I'm going to do plus 0.025 equal, and I'm going to divide that answer by 2 equal. So that gives me STO1, so I'm going to do STO1, and then I'm going to do 66 log, that gives me STO0, and I'm going to do plus recall 1 equal, so that's going to be 4.186, so it's going to be 4.186, that's going to be my mean, and my volatility is going to be equal to the squared variance divided by 2, and so that's going to be 0.25 squared, and I'm going to divide that by 2. So that's going to be about 3.12%. And so I'm going to have 3.12% here. So my normal distribution, or my log normal distribution, or not the log normal distribution, my log stock price is going to be normal distributed with a mean of $4.18 and a variance of 3.12%. Now, how do I compute confidence interval with this information? Well, because we're talking about logs, a log can be negative, and remember, we are working with a normal probability distribution here. So what do we have? We would have something that looks like this. We would have our distribution here, and we'll say we want, say, the confidence interval at the 95%. And you should remember this, at the 95%, what we have at 95%, z is equal to 1.96. At 99%, I think we have 2.33, and at 90%, we have 1.645. So this is going to be those are going to be the z-scores that we have, and essentially that is the distance away from the mean that we are going to be using. And so if we say we want to compute a 95% confidence interval, really what we're going to be we're going to be 1.96 standard deviation away from the mean on both sides, because we're working with a symmetric distribution. So our mean is going to be here. We're going to have 4.186, and so 95% means we are 1.96 standard deviation away from the mean on both sides, which means that we're going to be minus 1.96 multiplied by the standard deviation, which is 0.38%. Now, when we say 0.38% here, really what we are looking at is going to be a variance, because that is the term that we have here is the variance. We need to take the square root of that, so we need to multiply that by the square root of 3.12%, and on the other side we're going to do 1.96 multiplied by the square root of 3.12. Now you remember when I do this, implicitly I'm saying average, so it's going to be 4.18 minus that value, and here we're going to have 4.18 plus that value. That is essentially what we have here. Remember, that's the percentage value there. So it's going to be mean minus that value, and then mean plus that value, essentially. And so, and when we say 95% confidence, what we are saying here is that the area, the tail here, is going to be 2.5%, and the area, the tail here, is going to be 2.5%. And so that we have in the body of the distribution here, we have essentially the 95%. So this will be our 95% confidence that we have. So we are 95% confident that our mean return, log return, I should say, is going to be in the distribution. We should actually be careful here, because this is the log return. So our mean log stock price, not log return. Our mean log stock price will be in that value, in that range. And so to find the actual value for the stock price, we'll need to take the exponential of these values. And so how do we go about doing that? Let's do the math then. What do we have? We have the following. This here, if we pull a financial calculator, we are going to have 3.12%, and we're going to take the square root of that to find the standard deviation, and then we're going to multiply that by 1.96, and we say equal. And what I'm going to do is I'm going to store that 1. So this to store 1, store 1. And so the lower bound that we have here would be 4.18 minus recall 1, and that's going to be 4.18 plus recall 1. And so what do we have? 4.18 minus recall 1 equal, that's going to be 3.88. So here I'm going to have 3.88. And I'm going to say that that's less than or equal to the log of ST, and that's going to be less than or equal to, then we're going to do 4.18 plus, and then we're going to add recall 1 equal, that's going to be 4.52, so we're going to be 4.52. And so this gives me confidence interval around the log of ST, because it is the log of ST that is normally distributed with a mean of 4.18 and it is variance of 3.12%. And so that gives us the confidence interval around the log of ST. To find the confidence interval around ST, what we need to do is we need to take the exponential of 3.88 and exponential of 4.52. And the reason for that is because the exponential of the log of ST is equal to ST. So we could just get rid of that and write ST here. Now we could do the math here, just pull the calculator, and we would have the following. The lower bound, we could have 3.88 second function exponential. That gives us 48.42. So we would have 48.42 less than or equal to ST less than or equal to. Next is going to be to do the exponential of 4.52. So we're going to have 4.52. Let's do 52. Second function exponential. That gives us 91.83. So we're going to have 91.83. And this would give us a confidence interval around the future value of ST over the next 6 months. And the reason for that is because we use T here is equal to 1/2 for 6 months per our option value, and this will be the distribution for pi. So with a 95% confidence, we know that the security will be priced between $48.42 and $91.93. Now our security price is currently priced at $66, so that falls within that range as well. Okay, so that's an application of the use of the distribution, the normal distribution, to compute essentially confidence interval around our future value of the underlying that we have. Now, if we set, for example, a 99% confidence, what would we have? So with a 99% confidence, we would have the following. We would still build our greater probability curve. And with our probability curve, we would be somewhere at the tip tail end here. We would still have the mean. And the mean is not going to change, it's going to be 4.18. But we would have minus 2.33 standard deviation. And here we would have plus 2.33 standard deviation. And the standard deviation we know is the square root of the variance, so that will be the square root of the variance, which is 3.12%. And here we're going to do the same, multiply that by the square root of 3.12%. Now, what this gets us, and you remember that this is, again, 4.18 minus that, and it's going to be 4.18 plus that, right? So what we have here, let's call this A, and what we have here, let's call this B, would give us a confidence interval around the log of ST, because it is the log of ST that's normally distributed. At the 99% confidence, what we have is we have 0.5% at the tail here, and we have 0.5% at the tail here. That makes it such that we have 99% in the middle there. And so to find the distribution around ST, we would have ST less than or equal to the exponential of A exponential of B. And that would give us a confidence interval around the stock price at the 99% confidence. That's essentially what we would have. These values, the 95%, 99%, and the 90%. I think you should remember that. I think those are classic thresholds that we use with confidence intervals. So those are given. I think your book talks about 99% and uses 1.96, and essentially that's why at the 99% confidence and the 95% confidence we are 1.96 standard deviations away from the mean in both directions on a normal distribution curve or the standard normal distribution curve. All right, so that's what we're gonna have there. Next, what we want to do, perhaps because we've played with the standard deviation and we've played with this distribution that we have here, the next step is perhaps to compute the mean return. And the mean return, we just did that for the log normal distribution. Our mean return again is this value here, and we computed that accounting for all these terms that we have here, right? So it's the log of S0 plus R minus 1/2 of volatility multiplied by T. That's our mean, and that's why we're using the 4.18 as the mean return here. Also all the mean of the log price there. All right, what else do we need to play with? We need to work on Black-Scholes and the valuation of the option. So let's do just that. To do that, what I want to do is I want to write down the formula, and our Black-Scholes option pricing model formula is essentially saying that if you're valuing a call, your call would be equal to the stock price multiplied by probability ND1 minus the present value of the strike price multiplied by a probability that we refer to as ND2. And we said that D1 was equal to the log of the stock price divided by the strike price plus the interest rate plus 1/2 of the variance and multiplied by T, and we divide that by the standard deviation square root of T. And D2 is equal to the log of S0 divided by K plus the interest rate minus this time 1/2 of the variance, and then we have T, and we divide that by standard deviation square root of T. Now it just happens that D2 is also equal to D1 minus standard deviation square root of T. And or I should say, perhaps we should say, write it the other way around. D1 is equal to D2 plus standard deviation square root of T, and D2 is equal to D1 minus standard deviation square root of T. And if you remember the discussion that we had in converting our Brownian motion, we said we had B prime T, and we call B prime T as being BT minus standard deviation square root of T. By doing that, we actually force D1 and D2 to be different by standard deviation square root of T. Alright, so let's write the put option value. So the put option value is going to be equal to the present value of the strike, so it's going to be k exponential minus RT, that we multiply by n minus d2, and remember n minus d2 is also equal to that's 1 minus n d2, that's the same thing, and we do that, we're going to subtract the stock price, and we end up multiply 1 minus n d1, and that's going to be our put option value. So computing ND1 and ND2 is enough to compute both the call and the put option value for this option that we are working with. Now let's recall the data that we have. S0 is 66, strike price was 55, R was 2.5%, sigma was 25%, T was 6 months, or 1/2 of a year. Okay, so let's compute D1 and D2. So D1 would be equal to the log of 66 divided by 55 plus 2.5% minus, it's not minus, it's a plus, 1/2 of the variance, which is 25% squared, and multiply by t, which is 1/2, and we divide that by the standard deviation, which is 25%, and we have the square root of t is still the square root of 1/2 here. That's our D1, and so we can pull our financial calculator and do the math here. I'm gonna do the math backwards the way I would normally do. So I'm going to do the denominator first, and so I'm going to do 1/2 is 0.5. I'm going to take the square root of that, and I'm going to multiply that by 25%, which is 0.25, equal. So that gives me my denominator. So I'm going to store that 0. So I'm going to store that 0, and I'm going to do the first part of my numerator, which is 0.25 squared, that I'm going to divide by 2, equal. I'm going to add that to 0.025, equal, and I'm going to divide it by 2 again, so I'm going to divide it by 2 again, equal, and I'm going to store that 1, so I'm going to store that 1, and then I'm going to do 66 divided by 55, equal, and I'm going to take the log of that, and I'm going to store that 2. So my D1 should get rid of that. My D1 should really be equal to recall 2. Should use a different color here. Should be recall 2 plus recall 1 divided by recall 0. That would be my D1. And so I would be doing recall 2 plus recall 1 equal, and I'm going to divide that by recall 0 equal. So D1 will be 1.90465. Alright, so I'm writing here 1.190465, and D2 would be equal to D1 minus standard deviation square root of t. Now you remember that this is what I saved. This is the denominator here, so I call that I store that in 0. So I'm going to say recall 0. So it's going to be D1 that I just had here minus recall 0, and I will have my D2. And so I would go back to my calculator. I still have D1 here, 1.190465, and I'm going to do minus recall 0 equal, so my D2 would be 1.013689. So that'll be 1.013689, 1.013689, and that would be my my D2. Next, we need to find ND1 and ND2, and we're just going to read from the normal probability distribution. And the way we're going to go about doing that is as follows. Because the table will not have exactly D1 and will not have exactly D2, we are essentially going to do interpolation. And so D1 is going to be that, which means that we're going to round up. If we round up, we are going to go to 1.2, so it's going to be 1.2 by rounding up. And if we round down, we can round down to 1. Actually, let's do that in the next page here. So we're going to have the following. We're going to have 1.2, that is D2, this one that's rounded up. And we're going to have D1 here, and we're going to have 1.90, 19, that's 19 here. That is going to be 1.20 and 1.19. Remember, D1 is, let me write that here, D1 is equal to 1.19, what was that, 190465. 0465. Now we're going to have a probability for this value. We're going to have a probability for that value, but we're not going to have a probability for that value. So essentially this would be ND1, but then we're going to have N1.2, and here we're going to have N1.9, 1.19. And so from here we can compute ND1 by setting up an equality, and the equality is going to look something like this. The change between these values divided by the change between these values should be equal to the change between these values divided by the change between these values. Okay, so what do we have? We have 1.2 minus minus D1, essentially 1.190465 divided by 1.2 minus 1.19, that is this minus that, divided by this minus that, and that should be equal to this minus that, which is N 1.2, which we can read from the normal probability table, minus N D1, and then we are going to essentially divide it by the difference between these two values here, and that's going to be N 1.2 minus N, should have that here, and that would be minus N 1.19, and that would give us our equality. And so we can essentially solve for ND1, and so from here I'm going to call this whole term here, because those are values, let's call that A, is going to be equal to that term that we have here. So what I'm going to have is A multiplied by N 1.2 minus N 1.19. That's going to give me that product, and so I'm going to do N 1.2 minus that, and that should be equal to ND1. Actually, let's do that step by step because I skipped some steps here. Essentially, that's A here, this value here, this ratio here is A, is equal to the equality, so multiply that by 1.2 and 1.2 minus n 1.19 to get rid of the denominator on that side of the equation, and so this should be equal to n 1.2 minus ND1, and I need to isolate ND1, so I'm going to move ND1 on that side and I'm going to move ND1 over here, and I'm going to move this over there, and that's essentially what I'm doing. And so in doing that, what do I have? I have ND1 is equal to N1.2 minus A, which the difference between N1.2 minus N1.19, and that would be our ND1. And that's going to be interpolation, and that's going to give us a precise, a much more accurate measure of the probability ND1, and we could do that we could do the same thing for ND2. Now we have to be careful on how we interpret ND1, because ND1 is not the probability that the option expires in the money. That is not what it is. And again, it is not what it is because we made this adjustment when we were working with ND1 on our Brownian motion. Alright, so how do we do this? We need to pull our normal probability table, and we need to read we need to read N1.2 and N1.19, and so that's what we're gonna do next. Alright, so I paused for a second and I copied over a normal probability table, or a Z table, and that's where we're going to read essentially our our normal probability for 1.2 and 1.19. And so what do we have here? We have 1.2 and 0, so that gives us a normal probability table for 1.2. That's going to be 0.88493, so that's going to be, we use a different color here, 0.88493. so this is going to be this value because it's 1.2 and 0 here. That gives us N1.2 and minus A, and what we need here is 0.88493 minus 1.19, and so 1.19 is going to be 1.1 and 0.09, so that's going to be this value all the way at the end here. So that's going to be 0.88298. So that's going to be 0.88298. Now what is A? Let's solve for A here for a second. What we're going to do is we're going to do 1.2 minus 1.190465 equal, and if we're going to store that, I'm going to store that 0, and I'm going to do 1.2 minus 1.19 equal, I'm going to do the inverse of that, and I'm going to multiply that by a recall 0 equal. So A is going to be 0.9535, so we have 0.9535, that's what we have, and so we're going to sub that by 0.9535 there. So this value here is 0.9535, and we can compute our ND1. And so let's pull our calculator here and do just that. We're going to do the bracket first. So 0.88493 minus 0.88298 equal, multiplied by 0.9535 equal, that gives us that. Well, we multiply that by a minus sign, and we add 0.88493 equal. So our ND1 is going to be equal to 0.883071. 0.883071. So ND1 D1 is equal to 0.88371. That's going to be our ND1. We need to do the same thing for ND2. Now remember, to find ND2, we had these values. So how are we going to set up our problem here? Let's do that up here. Now for ND2, we remember that we're going to have the following. We're going to have 1.01 3689. Let's round that up. If we round that up, we get 1.1, and if we round that down, we get 1. And so what we're going to have here is we're going to have n 1.1. Here we're going to have n d2, and here we're going to have n 1. And so if we set that up in a similar manner that we had earlier, what we're going to find is essentially the following. We're going to have the ratio, which is going to be the difference between those two values, and so we're going to have 1.1. Actually, let's do this. I'm going to set it up all together at once. And so what I'm going to do is I'm going to say the probability of the upper bound, so it's going to be n 1.1 minus, now I need to find what a here is for d2, and a for d2 is going to be equal to 1.1 minus d2, which is 1.013689, and I'm going to divide that by the difference, so that's going to be 1.1 minus 1. And what I have in the bracket is n 1.1 minus n1, so it's going to be n 1.1 minus n1, and that's going to be it. And this should give me nd2, so this should be equal to nd2. And so what we need to find are n 1.1 and n1. So if we go to our probability table, we need to look for 1.1 and 0. That gives us this value here, 1.1 and 0. So there's going to be 0.86433, 0.86433, and we're going to go back all the way up here and move that value there. Hold on a second, I'm going to move this back here. There we go. Oops. And so this is going to be 0.833, so we're going to have 0.8, what was that value? 0.86433, 0.86433, and we're going to have 0.86433 there as well. And n1 is going to be what we have here. This is going to be n1, right, value here, which is 0.84134. So we're going to have 0.84134, and we're going to have a minus sign there. So we have the bracket, and we need to find what this value here is, and that's what we had there as a, essentially, or the other scenario. And so if we pull a calculator, what do we have? I don't know why I'm squeezing that up there. I could have done that down there, but let's go ahead and do that. So we have 1.1 minus 1.0, oops, 1.1 minus 1.01, 1.1 minus 1.013689 equal, we're going to start at 1, so I'm going to start at 0, store 0, and then we do 1.1 minus 1 equal, and then we're going to do 1 over x, and we're going to multiply that by, recall, 0, equal, so that gives us 0.863110, so that's 0.863110, and we multiply that by that, and we have our ND2. And so let's do just that. We have the following. We have 0.86433 minus 0.84134 equal, we multiply that by 0.863110 equal, we put a minus sign in front and we add 0.86433 equal. So our ND2 is going to be equal to 0.844487. So that means 0.844487. Let's verify that. 0.844487. That's going to be ND2. Alright, so now we have ND2 and we have ND1. And our ND1, I believe was this. This was our ND1. So now we can compute our call option value. So our call option value is going to be equal to the stock price multiplied by ND1. And you remember that ND1 was 0.88371. So that's going to be 0.88371. And to that we do minus the strike price, present value, and multiply by ND2. And ND2, we found that to be equal to 0.844487. So that's going to be 0.844487. And what that means is that we have an 84% probability that this option is going to expire in the money, essentially. And this relies a lot on the estimation of volatility. And so if the estimation of volatility is not accurate, your pricing of the option is not going to be accurate, and your probability is not going to be accurate either, because D1 and D2 are a function of volatility. Alright, so what do we have here? We have the stock price is 66 multiplied by 0.8371 minus the strike price, which is 55, and then we have the present value, or the interest rate was 2.5%, T is 1/2, and we multiply that by 0.8444, and then we have 87 here. And so what else do we have? We just do the math here and we find our call option value. And so for our call option value, what we are going to have is the following, using our Black-Scholes option pricing model. So it's going to be 0.025, that's our interest rate, divided by 2 equal minus, and then we take the exponential of that, so second function exponential, that gives us that, and then we multiply that by 55, which is our strike price, that's equal to 54.31, and then we multiply that by 0.844487 equal, that gives us 45.869814. I'm going to store that 0, so store that 0, and I'm going to write here that they store that 0, and then I'm going to do the stock price now. So for my stock price, what I'm going to have is the following. I'm going to have 0.88371 multiplied by 66 equal, and we're going to have 58.32, and I'm going to do minus recall 0 equal, so our call option value here is going to be equal to about $12.45. So our call option value is approximately equal to $12.45. That will be our call option value in this case. How do we find the put option value? For the put option value, we could either use the Black-Scholes option pricing model, for your put, or we could use the put call parity. And so, what does our put call parity tell us? We recall that the put call parity says that put plus stock is going to be equal to a call plus present value of the strike. And so put is going to be equal to a call plus present value of the strike minus stock. And so we have the call option value at 12.45. To that we're going to add the 55 strike present value at minus 2.5%, 1/2 for T because it's 6 months, and then we're going to subtract $66 from that value to get our put option value. And that would be a put option value. Now remember, in this context, the call has a probability of 84%, so it's going to be 84.44% probability of expiring in the money. So the put option value should be very small in this case. So what do we have for the present value of the strike? And that's going to be 55 for the strike there. The present value of the strike would be equal to the following. Let's bring back our financial calculator, and we would have 0.025, that's 2.5%, divided by 2, and then we put a negative sign, second function exponential, we multiply that by 55 equal, that gives us our present value of the strike. We add 12.45 to that, and that's the call option price, or the call option premium, equal, and we subtract $66 from that, so minus 66 equal. So our put option value would be equal to about $0.76. So our put is going to be $0.76 or 76 cents. And this is consistent with the probability, because this, remember, that is the probability that ST is greater than K. And that's because that is ND2. And if that probability that the option is going to expire in the money is that high, it simply means that the put option value is going to be really small. And so the good strategy here would be to sell puts and buy calls, essentially. All right, that wraps it up. You could play with this data and just compute the put option value using this formula, just to verify that you get the same answer that we got, the 0.76 cents. So if you did that, you would have 0.74 I don't like this. $0.74 that we have here for the put. All right. What else did we? Let's say this security paid dividend. If the security paid dividend, what we would essentially be doing is in the computation of D1 and D2, we will be correcting for the present value of the dividend. And so if we had a security that paid dividend, we would have the following. We would have D1 that would be equal to the log of S0 minus the present value of the dividend. And so that's going to be dividend here. You remember, let's say the company pays D dollars in dividends, you're going to have D present value RT, right? Where D is the dollar amount of dividend divided by the strike price. that is the correction that you'll be making on D1, and then you're gonna have plus interest rate plus 1/2 of variance, and you're gonna have t here still divided by standard deviation square root of t. So that would be D1. D2 would simply be equal to D1 minus standard deviation square root of t. That would work. And what else do you need? Your call option price would be equal to, remember that wherever we have S0, we need to correct that for the present value of a dividend. So it will be S0 minus D, present value of the dividend, and then we're gonna have N D1, and then we subtract the present value of the strike. There's no S0 here, multiplied by N D2. And that's the correction that would need to happen. And so let's say the company paid what was that? They say the company paid $3. Let's not say $3. Let's say $1, $1.25 in dividend, and the company paid that dividend 2 months into the life of the option. So D1 would be equal to the log of S0 would be 66 minus the $1.25 in dividend that we're getting. But because the dividend is coming in 2 months into the life of the option, we're going to discount that back 2 months. So we're going to do exponential of minus 2.5%, and 2 months is going to be 2/12 of a year, right? And that would be the present value of our dividend, and we would divide that by the strike price of 55, and we would do plus interest rate, and the interest rate was 2.5% plus volatility of 25% squared divided by 2 multiplied by 1/2. Now this t here for the expiration of the option stays the same. That doesn't change. The t here changes because the option comes 2 months. It doesn't come at expiration date, so you have to be careful how to discount that. And then you divide that by standard deviation, which was 25%, square root of t, and t here is still 1/2 because that option expiration t that we have there. Alright, well, this wraps it up. I'm sorry we had the keyboard getting in the way a few times in this video, but I've been having some issues with my technology here, so this is the best that we're going to be able to do in this case. I hope that was not too distracting, and I hope that the practice that we've done here you found to be helpful. Okay, so this is a really interesting unit, and that wraps it up for us. And I will see you in the next video to talk about the next unit.